Hello, this is Dr. Lukes, back for Chemie 3111, and we are looking at interpolation in this lesson. So we're going to be analyzing a different data set. It's, again, Alka-Seltzer and water reaction, but we've got this at 41.2 degrees Fahrenheit, and the data is analyzed in a slightly different way. In this case, this is all the curve fitting data, and we have here a curve fit. We have a couple of different curve fits. One is my estimate using a K1 for the first portion and a K2 for the full data set. And then we have what is estimated using just trend line. So we have several options here of how we can analyze this. And one is that we could actually just use linear interpolation. Now here's the problem. Look at this data. This data has a lot of noise. It's very poor quality data. And so if you connect these straight dots, it's not really even close to the points. If you look at two subsequent points, this one here is very near, this one's very above. Whatever you estimate is nowhere near what the actual curve fit probably is indicated by the dotted line. And only at a few points would this be a reasonable option. We also could use Lagrange polynomials. Now this is closer to being what we have shown here when we have the smoothed curves for connecting the dots, but you're taking 3 points and doing a smooth curve through those. And when I do that, it's a little better, but really it's still not very good. And the reason it's not good is because this is low quality data. There's a lot of noise to it. We could also use a curve fit. Now you have to decide what the best curve fit is, but if you have that and you have good values for K1 and K2, then that curve fit actually should be the most reasonable answer for an estimate at any point along there because it smoothed out the full data set. Now, if you adjust the number of points that you used, basically I threw out a couple of outliers, then you're going to get a better curve fit. But nonetheless, a curve fit for poor quality data will be your best way of doing an interpolation. But now let's look at a different data set. This is data for saturated propane. It has been studied by many different people, and the results of all of their data kind of average. This is from the national, well, NIST, but it's the national set of standards. And this is really nice, smooth data. So if you just look at one, so heat of vaporization data, which is this category H sub Fg, plotted as a function of temperature, you see that that's really nice and smooth. And so in that case, if I want to estimate the heat of vaporization, doing a linear interpolation would be pretty good. Doing a Lagrange polynomial would be awesome. I could do a curve fit, but it sort of feels like overkill. But this data is very smooth. That's why those work well. If you have something, though, where this is superheated propane data, and I have data at 2 bar and at 3 bar, and at a variety of temperatures and increments of 10, and I need to know the specific volume, for instance, of propane when the pressure is 2.38 bar, between 2 and 3, and the temperature is 7.56 degrees C. So in this case, neither the temperature or the pressure is listed on here. In this case, we use, it's called double interpolation, meaning I'm interpolating in 2 variables, but it's going to require 3 steps of interpolation. So first I might estimate for pressure of 2 bar what is the specific volume at 7.56 degrees C using interpolation. And linear interpolation on high quality data is probably fine. And then I would, at 3 bar, estimate what is the specific volume at 7.56 degrees C. Then take those two answers at the pressure of 2 bar and 3 bar and estimate what you get at 2.38 bar, again using interpolation. So that's 3 steps to estimate 2 variables using interpolation. So what I want you to do is I want you to try this, these 2 problems that I've given here, upload those, then look at how you would have used the data set from last week's experiment to estimate what would be the mass of CO2 evolved at, let's say, 38 seconds. Okay? And if you'll report those numbers, that's going to be Lab 9. Thank you very much for your time.